Hi Nana, welcome to our physics classes. How are you all? I hope you all doing good. And in our last class we had discussed the topics from waves chapter. And in our today's class I am going to discuss about the speed of a traveling wave. For this purpose I am considering a wave. I am considering a sinusoidal wave. Okay. And to find out the speed of a traveling wave, initially I am considering a fixed point. I am just focusing on this point and just observing this point on this waveform. Okay, initially the point is at this point. Okay, at this point I have taken the point, and after some time, as the time passes, what happens? This point moves from one position to another position. I have taken a dot at this point. Okay, what happens? This dot moves to a distance of delta x. This dot moves to a distance of delta x in delta t time, right? So here the time is t, and as this dot moves from this point to this point, the time here is t plus delta t. Okay, now from the wave equation, the motion of this fixed point is kx minus omega t, and this remains constant. As the phase remains constant, this kx minus omega t remains constant, because at this point and at this point the phase remains constant, it won't changes. I already explained in our last class. The constants atoms are phase, wavelength lambda, time period t, and amplitude. What we left with? Frequency, angular frequency, and nu, frequency. Okay. So as the wave moves in forward directions, all these constants are fixed. Okay, all these constants are fixed with respect to time, and the variables are y and x. In y-axis we have the particle displacement, and in x-axis we have wave displacement. So here the motion of this fixed point from this point to this point is given as kx minus omega t, which is constant. Now we know that the speed of the wave is delta x by delta t. This is the speed of the wave. Right? Delta x by delta t is the speed of the wave. And as the time changes, the position of this point or the position of this dot also changes, right? That is, x also changes. As time changes, x also changes, and phi remains constant. I already told this. All this terminology, that is phase, wavelength, time period, amplitude, frequency, angular frequency, and linear frequency, remains constant with respect to time, but this displacement of the particle and the wave changes. So here, as the time changes, this x changes and phi remains constant. Now this kx minus omega t can be written as k times of x plus delta x. Why? Because as of at this point x, and also at this point x plus delta x, the phase remains constant, and also at time t and at time t plus delta t also the phase remains constant, so that I can equate the coefficients. X is equal to x plus delta x, and this t equals to t plus delta t. Okay. Now from this equation, this kx minus omega t is equal to k into x plus k into delta x minus omega into t, minus into minus minus, minus into plus minus, omega into delta t. Now here you can cancel this kx into kx and kx, minus omega to minus omega t. Now we left with this k into delta x minus omega delta t, which is equals to 0. So this delta x is nothing but change in position and delta t is nothing but change in time. Okay, I am replacing these terms, delta x with dx and omega into delta t with dt, which is equal to 0. Now this k into dx is equal to, I am bringing this towards right hand side, minus will become plus. Now this dx by dt is equal to omega by k. What is this dx by dt? This is the speed of the wave. This is the speed of the wave, which is equal to omega by k, which is equal to omega by k. And what is omega? In our last class, omega is related with the time period, which is equal to 2 pi by t, and this wave number is related with lambda, which is equal to 2 pi by lambda. 2 pi by lambda. This is equation 1. This is equation number 2. Now substitute second equation in first equation. Substitute second equation in 1. Therefore the speed of the wave is equal to, what is omega? 2 pi by t by what is k? 2 pi by lambda. Okay, now you can cancel this 2 pi. Now you left with the speed is equal to lambda by t. Okay, so here this is the speed of a traveling wave. And the relation between the speed of a traveling wave and the angular frequency and this wave number is this equation, and the relation for the speed of a traveling wave and the time period and the wavelength is this equation. From these equations you can say that we require the time period for a traveling wave, and the wave will travel through a distance of lambda, which is nothing but wavelength. Here time period we require is to complete one oscillation. And in our next lecture I am going to teach you about the speed of a transverse wave on a stretched string. Okay, Nana? Whoever didn't subscribe to my channel, you just please subscribe and click on the like, and also share with your friends. Share my videos with your friends. Okay, Nana? Bye.